In this video, we're going to be looking at radiation uses, fission and fusion. And this is video number 3 of 3 for this topic. For our next video, you can either look at forces number 1, forces and their interactions, or if you're following along with the workbooks and tests, I recommend that you do the end of chapter test. Let's get right onto it. Okay, so background radiation. Background radiation is just radiation that's around us all the time. It comes from a variety of sources. Sources of background radiation include man-made sources and nuclear disasters. Radiation from the Chernobyl nuclear accident is actually still present over much of Europe. Other human activities give off radiation too, like nuclear power stations. There is also natural causes of background radiation, like certain rocks giving off radiation, like granite, which contains radioactive particles. Bananas, surprisingly, also give off radiation. And as well as this, cosmic rays from space are also a source of radiation. Radiation levels vary depending on your geographical location. Certain rock types are present in some places, whereas in other areas they may not be present. There are also some places like Chernobyl which obviously have higher radiation counts. So we can measure the dose of radiation which you get, and we measure radiation dose in the unit sieverts, and that's given the symbol SV. 1000 millisieverts, or MSV, is equal to 1 sievert, and the sievert is a derived unit of ionizing radiation dose in the International System of Units, SI units, and is a measure of the health effect of how low levels of ionizing radiation affect the human body. If you're following along in your revision workbook, pause the video now and complete task number 8. So, we're now going to have a look at some uses of radiation. Alpha particles can only travel a very short distance in air. Because of their low penetration, they cannot pass through smoke. This makes them excellent for smoke detectors. If smoke gets in the way, the detector will not pick up any alpha particles and the smoke alarm will go off. So here is a little diagram showing how a smoke detector works. Here we have an alpha radiation source, so we have a radioactive substance which gives off alpha particles. Those alpha particles travel this way and hit this detector, the radiation detector. For example, something like a Geiger-Müller tube. When the alpha radiation hits this radiation detector, the detector sends an electric current off to the alarm circuit. If smoke particles from, let's say, a fire get in the way of this path that the alpha particles take, then the alpha particles will no longer, or will hit this radiation detector with a much lower frequency, so there'll be less alpha radiation hitting this radiation detector. That'll then send a signal to the alarm circuit and say, oh, we're not getting very much alpha radiation, there's some smoke in the way, and the smoke alarm will go off. Beta particles are used in tracing, where a radioactive source is injected or ingested or eaten into the human body, and machines can track where these particles are going and where radiation is being emitted. Beta radiation is also used in thickness testing, where beta radiation is sent through a material and the amount of radiation which has been picked up on the other side is measured. So, this little picture here shows how that works. If you have a bit of metal being manufactured, let's say this sheet of metal, and you want to make sure that that sheet of metal is always the same thickness, what you can do is you can set up a radiation source and a detector, and the radiation source gives off beta radiation. The beta radiation is measured by the detector on the other side of the material, and then that detector is connected to a computer. The computer can detect how much beta radiation is hitting the detector, and if too much is hitting the detector, then the thickness of the material is too thin because a lot of radiation is going through. If the thickness of the material is too much, then there will be less beta radiation travelling through that material, and less beta radiation will be picked up, and the computer will know that the material is too thick, and it will adjust those rollers to make sure that the material that it's producing is thinner. Gamma rays are used to kill bacteria as well as to kill cancer cells. However, gamma rays are risky when it comes to usage in medicine. There is a chance that they can damage skin tissue and internal organs, or even give you cancer if they're used wrongly. So here we'll have a diagram which shows how gamma rays can be used to treat cancer. So what we have is we have this radioactive material, in this case it's cobalt, and gamma rays are shot into this sort of helmet device, and what scientists and doctors can do is point these gamma rays at a specific target. So if in this example it's in someone's head, if there's a tumour or a cancerous growth, doctors can aim these gamma rays at the cancerous growth and can kill that cancerous growth. And if the tumour cells or the cancer cells are killed, then it will stop growing and the cancer will go away. So gamma rays can be used to treat cancer. Is it actually safe to use radiation? For medicine, there are a multitude of risks for which using gamma radiation can cause harm. When gamma rays are aimed wrongly or are not strong enough, they can actually cause cancer to grow rather than causing the destruction of cancerous cells. Using beta radiation as tracers can also be dangerous. This is because beta radiation can cause ionization, and cells can become cancerous or even die to these sorts of doses of radiation. So beta radiation is good, but it has risks, and it is exactly the same with gamma radiation as well. So in medicine, they are good, but there are some risks. If you're following along in your revision workbook, pause the video now and complete task number 9. So now we're going to have a look at nuclear fission. Fission is the splitting up of nuclei. We have taught that nuclear decay is random and spontaneous, but fission rarely happens spontaneously. Normally it is induced. This means that fission has to be triggered, and this is normally us starting the reaction. So if you can think back to the last video, we taught that nuclear or radioactive decay, it's spontaneous and it is random. Random meaning any nucleus or any nuclei could decay next, we don't know which, and spontaneous meaning we can't change the rate at which it decays. But with nuclear fission, that changes a little bit. Yes, fission does happen in nature, but that's very, very rare. Normally for nuclear fission to occur, it's induced, and we induce fission. Fission normally occurs with larger nuclei, and the end product is two smaller nuclei, roughly being the same in size, as well as lone neutrons. After fission, the neutrons have kinetic energy, they move very fast. After a fission reaction, there is also gamma radiation emitted. This is energy which is being released. So, let's have a look at this example of nuclear fission. A neutron is propelled into the nucleus of an unstable isotope. This makes it even more unstable. So here we have a nucleus, and in the nucleus we have protons and neutrons, and this is an unstable nucleus. So as you've just seen by that animation, this neutron has been fired into the nucleus. Now it's even more unstable. Neutrons are emitted, gamma rays are emitted, and the nucleus splits into two smaller, almost equal in size nuclei. So as you can see, the previous nuclei has split into two daughter nuclei, and we'll call these new nuclei daughter nuclei. So you can see that we have this new nuclei here and this new nuclei here. But we also have these two neutrons which have been propelled as well. And on top of that, we'll have gamma rays. So this is what you need to know. So you need to know that during nuclear fission, two daughter nuclei are created from one bigger starting nucleus which was unstable. And when a neutron is fired into that nucleus, it becomes even more unstable and splits, releasing two neutrons and gamma rays. Energy is released in fission, both kinetic energy within the neutrons and thermal energy. So fission is hot, You can feel the heat from fission reactions, and that's the way that it gives up energy. But the neutrons also have kinetic energy, and of course there's gamma rays, which are very high energy electromagnetic waves. To start fission, a neutron is fired into the nucleus of a larger, already unstable atom. This means it is now even more unstable, as it is yet another neutron, and it needs to split and release neutrons. This is done by us. It is inducing fission. So in nuclear reactors, in nuclear power stations, fission is induced by firing neutrons into the nuclei of unstable atoms. And that then causes fission to happen. Often, fission then continues in a chain reaction. When neutrons are released, they can cause chain reactions. This is because the neutrons, which collide with other nuclei, then cause those nuclei to split as well. So these neutrons may collide with other nuclei of other radioactive substances. When this happens, the receiving atoms then undergo fission as well, and then the whole process repeats. This is actually how nuclear bombs work, like those dropped in Hiroshima and Nagasaki. So fission is a chain reaction, or it can be a chain reaction if there's lots and lots of undecayed nuclei together. So if you induce fission, the nuclei splits into two daughter nuclei, but as we've seen from the animation before, there's also two neutrons being ejected as well. And those two neutrons can then go on to hit other nuclei, which then split themselves and then release even more nuclei, which then hit other nuclei, and so on, so on, so on. So fission is a chain reaction. We're going to watch a little video now.
Hello there. We're going to be talking about nuclear fission. Nuclear fission is the splitting up of a large, unstable nuclei into two smaller daughter nuclei, releasing large amounts of energy at the same time. Nuclear fission can happen in nature. This is called spontaneous fission and is very rare. Nuclear fission can also happen in a man-made setting. This is known as induced fission and works by firing a neutron at the unstable nuclei to make it even more unstable, and hence it splits up after the neutron has been absorbed. Let's take this unstable nuclei for example. If we take a neutron and fire it at the nuclei, it then splits up into two daughter nuclei which are roughly equal in size, as well as two neutrons. As we've just seen, there are also two neutrons released. Gamma radiation is also released. This is a high energy wave and carries away a large amount of energy. But what happens to the neutrons which have been ejected? The neutrons which have been ejected go on to induce more fission. More nuclei split, releasing more neutrons, and the chain continues. Scientists call this a chain reaction. It is important to note that this can't happen for all atoms' nuclei. It can only happen for unstable nuclei. Unstable nuclei can come from isotopes of uranium and plutonium, where there are more neutrons than what is stable. Uranium-235 and plutonium-239 are two isotopes commonly used for fission reactions. This could be for use in reactors, like in power stations, or even for use in nuclear weapons.
Okay, so that explained what we've already went through about how fission works and how fission can then induce more fission with the releasing of neutrons, and we'll call this a chain reaction. The chain reactions of fission can cause lots of energy to be released, and this can be handy for generating electricity in power stations. In nuclear power stations, the very intense heat created by the fission process can heat water. This water is then turned into steam, which drives round turbines as it is under pressure, which generates electricity. But we can't allow fission to go on uncontrolled. So we need to control nuclear power station fission. It's important that the rate of fission is controlled within power stations, as fission out of control can lead to nuclear disasters. Control rods absorb neutrons, meaning they cannot enter more nuclei and trigger more fission. Lowering the control rods into the reactors therefore slow down the rate of fission and can control the rate of fission. I'm going to watch another short video now.
Hello there. We're looking at nuclear fission in power stations and in weapons. As we have already seen, fission is a chain reaction, and if left uncontrolled would continue until all of the fuel, or unstable nuclei, were split, and massive amounts of energy would be released. We can use fission in power stations to generate heat. This heat then turns water into steam, which drives turbines generating electricity. However, we need to control this heat and the amount of energy being released by nuclear fission. This is where control rods come in. Control rods are lowered into the reactor and absorb neutrons. Because the neutrons are being absorbed, they cannot continue in their path and induce more fission with other nuclei. Nuclear power has advantages and disadvantages. An advantage is that it is very clean. It does not produce greenhouse gases. Another advantage is that, although it is not renewable, it will last us a very, very long time, as you get a large amount of energy from a small amount of fuel. Disadvantages include the fact that you need to dispose of nuclear waste. The waste products are highly radioactive, so need to be buried deep underground. There is always the risk of a nuclear disaster. If a nuclear power station has a problem, there is a possibility that a very large area around the power station may be inhabitable for a large amount of time, as well as irradiating the people and animals which live there. Nuclear fission in weapons is uncontrolled. This means a very large amount of fuel is went through quickly. Nuclei split quickly, meaning a large amount of energy is released, a very large amount of heat, and dangerous gamma rays are all released in a very small time.
So, control rods in nuclear power stations absorb neutrons, and that then stops the chain reaction from continuing because more unstable nuclei don't absorb those neutrons and then go into fission themselves. As you can see, as well as in power stations, they can also be used in nuclear weapons, and in nuclear weapons, nuclear fission is completely uncontrolled, so the weapons can do as much destruction as what they can, which is a very horrible thought. Nuclear war is a really horrible thought, so let's move on quickly. Can you draw a diagram showing fission and the chain reaction which is set up because of it? Can you draw a diagram to show nuclear power stations generating electricity and the use of control rods? Let's hope you can, because that will be good practice, and if you can do that, it shows that you understand this topic. And you can have a go at that in task 10 in your workbook if you pause the video now and get on with that. Okay, moving on. The next thing and the final thing that we're going to look at is nuclear fusion. Nuclear fusion is the joining of two light nuclei to form a heavier nucleus. In this process, some of the mass may be converted into the energy of radiation. In nuclear fusion, two light nuclei, like two hydrogen atoms, merge to form a heavier nucleus. During this process, some mass is actually converted into energy. This is the process which happens in the centres of stars to form new elements from atoms and nuclei which have been put under so much pressure that they merge. Nuclear fusion is not a chain reaction. This phrase can only be used to describe fusion. Only be used to describe fission. So fusion, not a chain reaction. Only fission is a chain reaction. So you can see by this little animation here that we take two light nuclei, hydrogen 3 and hydrogen 2, combine them together, which is fusion, and then we get helium and a neutron. Complete task 11 in your atomic structure workbook and pause the video now. And once you've done that, you have finished. Congratulations, we've finished the topic of atomic structure. If I were you, I would take the test, see how much you've learned so far, and yeah.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.